Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series, BSc Applied Electronics. This module deals with the oscillators and amplifiers. The content of the module is AC characteristics, differential amplifier and its gain, and CMRR. We have already seen what are the AC characteristics: frequency response of operational amplifier, stability of an operational amplifier, and slew rate. And in frequency response, we have discussed about how the gain of the operational amplifier is decreasing for the higher range of frequency signals, and ideally the bandwidth to be infinity. For the ideal operational amplifier, the bandwidth must be infinite, but practically, because of the roll off rate for the higher frequencies, the bandwidth is reduced. So, for which we have seen the frequency compensation techniques also in the previous session. So, one of the frequency compensation technique we have discussed is dominant pole compensation. In dominant pole frequency compensation technique, the pole is introduced, and because of the pole we got a corner frequency called F1. At F1, the gain of the operational amplifier touches 0 dB line, and the gain is reduced at the rate of -20 dB per decade. So, this graph shows the dominant pole frequency compensation technique, and this graph shows the frequency response of the operational amplifier with 3 capacitance effect in the internal circuit we have considered. And with these 3 capacitance effect, we got F1, F2, F3, the frequency from the capacitance effect seen internally or externally in the operational amplifier. Because of these frequency terms, we got the roll off rate as -20 and -40 dB per decade, and finally the -60 dB per decade. And this is just our consideration, our assumption that only 3 capacitance effects are present in the internal circuit. If the capacitance effect is more, then the roll off rate is also increased by, for every 10 times increase in the frequency, the roll off rate is -20 dB per decade. And the next compensation technique we are going to see is pole zero compensation technique. In pole zero, we are introducing a pole and a zero by connecting externally the resistor and a capacitor to the operational amplifier. If pole and zeros are connected, then the response of the operational amplifier with this pole zero compensation technique is like this. At F2, the gain touches the 0 dB line at F2, and we know that these are the frequencies F1 less than F2 less than F3 caused by the capacitors present internally. And in the previous case of compensation technique called dominant pole, the gain in dB touches the 0 dB line at F1. Here at F2, how this F1 is cancelled is because of this 0 we have introduced, and by connecting the external components R and C. So, this 0 which also produces the frequency F1, and there is a pole also introduced by externally connecting the resistor and the capacitor. So, both the poles and pole and 0 has the corner frequencies F1. So, both will cancelled out and the gain touches 0 dB at 2, not as in the case of dominant pole at F1. So, the bandwidth is increased in the case of pole 0 compensation technique. It is F2 minus F1. So, this is the advantage of the pole 0 compensation technique. Next compensation technique is internal compensation technique. We have seen external compensation technique called dominant pole and pole 0 compensation. Internal compensation has the capacitance internally fabricated. The value of the capacitance is 30 nanofarad. So, with this capacitance, the effect is the bandwidth is increased and we got a lower closed loop gain than the open loop gain. Next, we are going to see about differential amplifier. We have to recall we have seen this as the one of the circuit for closed loop configuration in the first lecture. So, what is an amplifier and which feedback is given to an amplifier, we have to recall, and what are the assumptions we have made before calculating the gain of the differential amplifier, we have to recall. So, we know that for an amplifier a negative feedback is given. Here the portion of an output is given through the resistance R3 to the inverting terminal, and so if the feedback is given to the inverting terminal, then it is a negative feedback. Negative feedback is given, and what are the assumptions we made? The current drawn by these two input terminals is assumed to be 0, and the potential at these 2 points, negative and positive pin, is equal because of the virtual ground concept. So, now we are going to derive the gain of the differential amplifier circuit, and in this circuit we are assuming this R3 and R4 are equal, and these two input resistance are also equal, R1 and R2. If R1 and R2 are equal, R3 and R4 are equal, then we will get the output as R2 by R1 into the difference in the input voltage. So, now this is the differential amplifier circuit for which we are giving the input signal at both the input terminals. Here V1 and here V2, and we have to give a negative feedback from the output signal through the resistance. I make it as RF, and what is this resistance? It is our compensation, which compensate the effect produced by the input bias current, which is equal to the resistance at the feedback, and these two resistances are assumed to be equal, and we know that these 2 points have same potential called V3. And now we are going to calculate the gain of the differential amplifier circuit. So, what is this current? Say it is I1 and this current as IF. So, for I1 I can write the equation as V2 minus V3 by R1, and this feedback current I can write it as plus. So, from the output it is going at this node we are applying KCL. So, the sum of the current flowing towards this node is written here. So, IF is V0 minus V3 by RF is equal to 0. From this equation, V2 by R1 plus V0 by RF minus V3, it is taken out and it is 1 plus R1 by 1 plus RF is equal to 0. And for this loop at this node, if we apply again KCL, the current through this resistance as I2 and this current as I compensation. So, the current I2 is flowing towards this node and compensation current is flowing away from the node. So, both are reversed. So, I2 is given as V1 minus V3 by R1 minus V3 by or compensation, or it is equal to RF is equal to 0. From here V1 by R1 is equal to V3 as common 1 by R1 plus 1 by RF. So this same term we are seeing in both the equations. So substitute this term in this equation. So we will be getting V2 by R1 plus V0 by RF is equal to V1 by R1. From this equation we can obtain V0 by RF is equal to V1 minus V2 by R1. And what is V0? It is RF by R1 into V1 minus V2. This minus for V2 is because V2 is given to the negative terminal. So this is the output of the differential amplifier circuit. So we have to assume these two input resistances are equal and these two feedback resistance and the compensation resistance values are equal, and so we are obtaining the output voltage as RF by R1 into V1 minus V2. So for this, based on the difference between this input voltage V1 and V2, we will be getting a plus or minus sign here. So if the difference is negative, you will be having negative sign. If the difference is positive, having a positive sign. So you can include a plus or minus sign. So this is the gain of the differential amplifier circuit. And when we see about the differential amplifier, we will be discussing about the common mode rejection ratio. So what do you mean by common mode rejection ratio? For which we have to know what is the common mode gain, what is the difference mode gain in the differential amplifier circuit. So the output of the differential amplifier is depending upon not only on the difference between the input signal, but also depending upon the average value of the input signals. For example, if the input voltages, say V1 is 50 millivolts and V2 is 100 millivolts, the difference is 50 millivolts. And for the next case, if the input voltage V1 is 500 millivolts and V2 is 550 millivolts, again the difference is 50 millivolts, but the average is different. So the output voltage is not the same for both these two cases, because the output voltage is depending upon the average value of the input voltages also. So this average value is given by the common mode voltage VCM is equal to V1 plus V2 by 2, and the output of the operational differential amplifier is A1 into V1 plus A2 into V2. Why it is the amplification factor is considered as 2, A1 and A2? Because there may be the mismatch of the transistors inside the operational amplifier. Because of the mismatch, the gain of the differential amplifier for the input voltage V1 is different from the gain of the amplifier for the input voltage V2. Here A1 is the gain for the input voltage V1 and the next input terminal is grounded, and A2 is the gain for the input voltage V2 for the next with the next input voltage grounded. So because of the imbalances, we are having this output for the differential amplifier. We will have break. Welcome back. So we have discussed the differential amplifier circuit and the gain of the differential amplifier circuit previously. So what is the use of this differential amplifier circuit is, if the difference between these two input signals is very low in the range of millivolts, by using this amplifier circuit and by designing the amplification factor by the resistances RF and or compensation, we can amplify the millivolts range of the input signal into a volt range. So, a slow varying input signal can also be amplified 100 times at the output by the differential amplifier circuit. This is one of the major advantage or major use of the differential amplifier circuit. So, now we are discussing about the gain of the differential amplifier and the output of the differential amplifier, which is depending not only on the difference in the input voltages but also on the average values of the input signals. So, this average value is called as common mode voltage. It is given as V1 plus V2 by 2. Because of the mismatch, the gain of the amplifier with respect to the first input voltage, say V1, is different from the gain of the differential amplifier for the next input voltage V2. For both the cases, the other input voltages are grounded, and this is because of the mismatch of the transistors inside the operational amplifier. So, what is the difference in the input voltage? It is given as differential voltage Vd as V2 minus V1. This V2 and V1 are the voltages given at the input terminals of the differential amplifier, and we know that the common mode voltage as V1 plus V2 by 2, and V1 from this equation it is derived as VCM plus Vd by 2 and V2 as VCM minus Vd by 2. So, substitute these equations V1 and V2 in the first equation called V0 is equal to A1 into V1 plus A2 into V2. We will be getting the output voltage as ADM Vd plus ACM VCM. What is ADM? It is the difference mode gain of the differential amplifier, and Vd is the difference in input voltage, and this ACM is the common mode gain of the differential amplifier, and this VCM is common mode voltage, and ADM is given as A1 minus A2 by 2 and ACM is A1 plus A2. So, this is the output of the differential amplifier. V0 is the difference mode gain with the difference in voltage plus common mode gain with common mode voltage. So, from this we can see what is the common mode rejection ratio. So, it is defined as, this is an important area of the differential amplifier circuit, it is defined as the relative sensitivity of the operational amplifier to the differential signal as compared to the common mode signal is called common mode rejection ratio CMRR, and gives the figure of merit rho for the differential amplifier is modulus of ADM by ACM, and this ACM must be equal to 0, and so the CMRR value will be infinity ideally. So, higher the CMRR, better is the operational amplifier performance. And next is slew rate. So, what is slew rate? Ideally the slew rate must be infinity. This factor is also to be infinity ideally, but practically it is not so. The slew rate is defined as the maximum rate of change of output voltage caused by the step input voltage and is usually specified in volts per microseconds. What do you mean by this slew rate? So, how instantaneously the output changed for change in the input voltage. So, how much time it takes, the output takes for to be changed for the change in the input voltage is said to be slew rate. So, it is checked by giving a standard input signal called a step input signal, and it is specified always in volts per microseconds. Normally it takes microseconds for change in the voltage range. So, it is volts per microseconds. For example, if 1 volt per microsecond specifies that the output rises or falls by 1 volt in 1 microsecond, ideally the slew rate is infinite. But practically it is not so because of this reason. There is usually a capacitor within or outside the operational amplifier to prevent oscillation. Just now we have seen in the frequency compensation techniques, we have added the resistor and a capacitor to compensate the effect seen in the frequency response of the operational amplifier, or you can say that to increase the bandwidth of the operational amplifier circuit and also to reduce the closed loop gain than the open loop gain, we are introducing a capacitor. In the internally compensated capacitor, already there is a capacitor inside, it is fabricated with the value of 30 picofarad. So maybe because of this reason, the capacitor which prevents the output voltage from responding immediately to a fast changing input. The rate at which the voltage across the capacitor increases is given by dVc by dt is equal to I by C, the maximum current flowing across the capacitance by the capacitance. So this is a simple response of the operational amplifier to explain about the slew rate. So to respond from the initial state to the final state, or to reach this 10 volt of peak, the operational amplifier takes 0.667 microseconds. So for this response, for this operational amplifier, if we calculate the slew rate, then it is 10 volts per 0.667 microseconds, it is 15 volts per microseconds. This is the slew rate. So ideally the slew rate must be infinite, which means that it should not take much time. It should not take time is equal to 0 unit. At this time the output must change for any change in the input voltage, but practically this is the case. This is taking microseconds for reaching the output voltage or 90% of the output voltage. And the slew rate is given as, the slew rate must be greater than or equal to 2 pi f, the maximum voltage, where f is the operating frequency and Vm is the peak amplitude of the waveform. And now, to test your knowledge gained from the first session in the operational amplifier, we will design an inverting amplifier. Inverting amplifier for the gain minus 10. We know that the gain will not have any unit, and since it is an inverting amplifier, the gain has a negative sign. If it is not mentioned like design an inverting amplifier, instead of that design an amplifier for the gain minus 10, we have to design this inverting amplifier because the gain has a negative sign. So now we have to recall the formula, the gain of the inverting amplifier as minus Rf by R1, and which is given as minus 10 here. So minus and minus will get cancelled, and R1 we have to assume as high. In this case we are assuming 10 kilo ohms, and substitute this value, you will be getting Rf as 100 kilo ohms. So what is the value we have calculated? And we know that the signal Vi is given through the resistance R1 to the negative terminal, and the feedback resistance Rf is connected to also to the negative terminal. Positive terminal is grounded, and this is output voltage. So here this R1 is taken assumed as 10 kilo ohms, and this Rf as calculated as 100 kilo ohms, and so the output voltage is 10 times greater than the input voltage. So this is the gain design of the inverting amplifier for the gain minus 10. If it is for design an amplifier, here the type of the amplifier is not mentioned. Design an amplifier for the gain 5, for the gain only 5, it is plus 5. So you have to design what amplifier? Non-inverting amplifier Vi, and since it is a non-inverting amplifier, the signal is given to the positive terminal, and for the amplifier we know that the feedback is given to the negative terminal, and the resistance R1 is connected to the negative terminal and other end is grounded here. And what is the gain of the non-inverting terminal? The formula is 1 plus Rf by R1 is equal to 5, which is given. Always we have to assume R1 as 10 kilo ohms. So substitute this value in this equation. So, it is 4 into 10 kilo ohms, it is 40 kilo ohms. So, RF is 40 kilo ohms. So, you can give these values in the circuit. So, this is an important question you can expect. Design an amplifier for the gain minus 10 or for the gain plus 10. So, based on the given parameter, you have to select an amplifier, whether it is an inverting amplifier or a non-inverting amplifier. And finally, we have to summarize what we have seen in this module. And we have seen the frequency compensation techniques, dominant pole and pole zero compensation. And we have discussed about the differential amplifier circuit and the importance of the differential amplifier circuit, and we have derived the gain of the amplifier, common mode rejection ratio, slew rate, and design of inverting amplifier and non-inverting amplifier here. To check the knowledge, we have questions: what is the ideal value of the slew rate and the CMRR, define CMRR, design a differential amplifier for the gain 5, and differentiate the dominant pole and pole zero compensation techniques in frequency response of an operational amplifier. So, you can include the design of the differential amplifier for the gain plus or minus 5. If it is not mentioned as differential amplifier, simply instead of that simply an amplifier, if it is plus or minus, you have to design which amplifier. It is a differential amplifier, because in the differential amplifier we know that we will be having plus or minus based on the difference between the two input voltages. Whichever may be higher, the difference may be the positive or in the negative region. So, the gain will be having plus or minus. With this, we conclude this session. Thank you.